Welcome, everybody. My name is Bente Lilja. I'm going to be your host in today's ILIAD webinar series that will be on ocean modeling in the frame of digital twins. And to begin with, I will introduce the program, and I will talk about the ILIAD project a little bit before we are introducing the many experts that are going to enlighten us on ocean modeling. So I start by sharing my screen, and you will see our experts. We will start with Ingrid Ellingsen on ocean modeling in general. Sylvain Cailleau will talk about Copernicus services and digital twins. Katerina Spanoudaki and Paulo Leitão will give us some examples on how we are using various products related to the ILIAD digital twins. So yeah, here you see the actual titles of the talks, and I will introduce the speakers as they are in line in the program. But first, I would like to introduce you to ILIAD project very quickly. So, and myself, I am the innovation manager of ILIAD, and I have a long background in Earth observation in general, and also being involved in sea level monitoring and tsunami warning system, etc., other activities related to the sea. Now, digital twins are of the ocean, provides a virtual environment representing the ocean and capable of running complex and predictive management scenarios. The innovative system integrates across many different disciplines, sensors, models, and digital infrastructures. And key in ILIAD is that we want to make, and we are making all of this interoperable in a data-intensive and cost-effective way. So ILIAD in the seashell is that we are enabling an ecosystem of interoperable twins, so multiple twins, and we are using existing systems, and we are also creating new observations and material and resources to build these twins. All of this will be made available on an open marketplace so that the communities can be using all of these results and combining it in different ways. And of course, we are providing solutions to many of the general challenges related to sea activities. So here you see some examples and some areas of the digital twins of the ocean that we are covering. It's both thematically varied and also on different locations. In ILIAD, very quickly, it's a huge investment from the European Commission, and we are 56 partners and are going to spend close to 18 or 19 million euros. The project is 3 years, and we are a little bit into the second year. So the first speaker will introduce us to ocean modeling in general. And Ingrid is working as a senior scientist in SINTEF Ocean, and her main qualifications is sonography, and she's an expert on one of the models that we are using, hopefully going to use more of in ILIAD, the SINMOD. And she has experience on applying this in, for instance, aquaculture. Ingrid, I'm very happy to have you here with us today. And I would like to give you the floor so we can learn about ocean modeling.
Thank you. I was just starting to share the...
Share the screen. Yes, and we are encouraging you to ask questions. So please do that in the chat. And we are also doing some polls in between here, and we will be very happy if you are participating in that. Okay, I give you the floor again, Ingrid.
Thank you, and thank you for giving me this chance to present. As you see from this first slide, I have changed the title a little bit. As you said, I will speak about modeling, but I think I want to focus more on what we have been working with, mostly with, and where I have my largest experience. So I'll talk a little bit about high resolution modeling and some application, how we use these models, which I think is important for the physical twins, and also some of the challenges we face when we're working with this. As Bente mentioned, we are working with a model framework called Thematic. This is an in-house developed model code, and it is a coupled physical and chemical and biological model system. It's developed here at the SINTEF Ocean in Trondheim, and in recent years we also have the people from the university here participating and developing the system. So this is a regional model system, which we start usually at 20 kilometers as model domains, and then we go down to really high resolution models, down to 32 meters. I will get back to that. So this is a model system that we run a lot in the high class mode, where we're doing different studies in different projects, but we also have applied it in an operational. We can run it in an operational way to provide forecasts that we have done in several projects. So for my background, I'm doing modeling, and my background is mostly in coupled biological and physical modeling. But if we start with a single model framework and focus on the physics, we have a hydrodynamic module that is based on the primitive equations, giving you the current, temperature, and salinity. And we also have an ice model going online. With that, we have a, So this is the hydrodynamic model. But what I think is best special about Thematic that it's been developed as a coupled biological and physical model system since the 1980s. So we also usually always working also on the biology or other modules in addition to the hydrodynamic model. So the ecological model system includes typically 14 to 16 states. We have states for nutrients, phytoplankton, zooplankton. We also have included here just simplified version, but it's 14 states, and we have also microbial processes in there, and also a module for benthic and phytos and so on. We also have modules here within the system for the carbon chemistry and also oxygen. And then we have some more specialized models for different species, like the blue mussel, seaweed, or more specialized towards aquaculture. We also have models for migrating coastmods for rivers, and we also have a population model for sea life. And I mentioned this, and I will just show you an application of this and how this how this actually works. So then, in this case, we just run the hydrodynamics and this sea life model and this salmon coastmod migrating model. We start here. You can see the west coast of Norway, and you can see there's a concentration here. And this concentration is sea lice as individuals per square meter. So what we have done here is actually release the sea lice from all the fish farms according to accounts of female sea lice on the farm. And then we calculate the development of this sea lice, because the sea lice has a pelletary phase. So we calculate, so we simulate the development of the larvae from their larvae until they are infectious crocodiles, and that's when they can stay on a smolt and also affect the wild smolt. So this shows you just the releases with the fish farms that are close to the coast, and you can see it's close out to the coast with the brackish water outflows, and then it goes into the coastal current. A second step here is to model the migration of the postmods. So the postmods are migrating from the different rivers along the Norwegian coast. So this is an example of our modeling. This is one smolt going out in the fjord, and you can see it follows the currents and then it moves out of the fjord. It takes a bit of time, but you can see it's blue colors and red colors is where it actually meets sea lice. So this is where it is exposed to sea lice pressure. And the end goal in this actually system is to have an estimate of a number of sea lice on the smolt in the end. Because what we want to know is how the fish farms in Norway can affect the mortality of the post-smolt on wild salmon as a result of the release of sea lice from the fish farm. So this was one application. Another application we work with is the location of fish farms. One of the new things is to have these fish farms in open water, offshore fish farming. They're talking about concepts that are quite large. Here's one concept called smart fish farms. You can see the size of it. So work here has been analyzing quite large data sets, and we also produced a large data set of similar data, 10 years of data, where we analyzed different environmental conditions to find good location for this farm. Just an example, this is a mean value of the temperature. That is interesting for them to find a good location. But again, since sea lice is important in Norway to see the effect of that, we also want to find locations so that if there is an outbreak of sea lice in this fish farm, the sea lice should not reach the existing fish farms along the Norwegian coast. And the same, we are doing the modeling the other way. We look at how diseases or sea lice can be released along the coast and how then they can reach potential locations of offshore fish farms. This is another example. But a little bit to the challenges. So here you can see a picture of how this looks outside the coast of mid-Norway. Here you can see a fish farm, and you can see it's quite close to land, and there's another fish farm over further out. And you can see that this is a quite complex environment, and this is something we have to work with if we're going to produce some realistic environmental conditions in ocean models for this fish farm. So to give you an example, we have done this simulations with 32 meter resolution. So you can see here is the current speed, blue is low currents and red is high currents. And you can see the tides going back and forth. All these names are different fish farms in this area. It's again outside in Norway. But what you can see is how this local topography is affecting the currents and why we have to go down to really high resolution to try to resolve it, which we need for some specific problems related to aquaculture. Going to another challenges, our challenge is this is actually from a really nice. We had some really nice days last week, and when we have nice days, we also have nice satellite images. So this is from Sentinel-3. So this is estimate of coastal A. You can see again Sonnenfjord. This is the coast of Norway, and then you can see the bloom outside here. And one of the reasons I like to see this is they are very dynamic, very beautiful, but they're also very complex, and it also represents a challenge when we are trying to model this with a combined physical biological modeling. So I'll just guide you through some examples. This is an example of zooplankton. This is something we produce with a model. So this is a snapshot of biomass of zooplankton outside in the Norwegian Sea, and you can see you get some structures. But if you zoom in and we play with different resolution, we see that this is 4 kilometers, and if you go down to the 20 kilometers, we don't see any processes at all. But if we go at higher resolution, we can see that the biomass distribution is getting more complex, and the eddies or the mesoscale dynamics are looking more realistic. But the problem is that if we even go to even higher resolution, we can have a picture like this. You can see this is within the square outside Lofoten in Norway, and you can see really, really deep details and large patchiness in the distribution of the zooplankton. This is also something we work in a project, because zooplankton is also can be a harvestable resource, and we will not want to know the amount. We want to know where we should go fishing for it, and then we also want to know how this is distributed. But this is a model result, and we need to know a bit more. Is this a realistic patchiness? Is the physical processes correctly represented? And we also have to look into the biological processes. And then a question that we have raised: what is the correct level of tightness. Is this a modular artifact, or is this something that's actually new? If I have time, I just had another example showing this with other problems of actually opportunities. This is just showing, we're looking into the potential of growing seaweed in Norway. It's done already, but we are also looking at where it can be grown. So this is just showing a cultivation potential that's calculated from the model system. So it tries to guide it where the greatest potential is. And you can see there's great potential out in the deeper sea where you have more nutrients available. But you can also see there's a high variability closer to the coast. We also look at seaweed as a potential carbon capture way. So this is just showing that we can also calculate how this carbon capture can be done with seaweed and how much carbon they can capture to calculate the CO2 uptake in seaweed and see a similar map of that. That is of course related to the potential of growth. Yeah, I want to mention the last slide here, something about dissemination observations, because that's also relevant. We're working with NTNU that is working on the observational pyramid, where you have the satellites covering a large area, and then you go to the drones, surface vehicles, AVs, and so on. And these are definitely different levels of observations that you can utilize and use in data simulation of the model system. But this is quite complex. There's different levels, the different types of data that is simulated in different way in the physics and biology of the model framework. And we also have the different, again, scales. How we're going to simulate this into the high resolution models or the quarter resolution models and what effects that have. This is something of the topics that you're working on, such as antenna. So, yeah.
Thank you very much, Ingrid. That was very impressive, and I think you illustrated the many different applications areas of ocean modelings and what you can see with high resolution. So thank you very much for that. I will share with you now. I did a poll while you were talking to gauge what we are, what the audience know about and how they are using, if they are using ocean modeling. And I share with you the results. We asked, are you using ocean modeling in your work? And 58% of ocean modelers here, you can see. And we have quite a few that are both learning and also interested in ocean modeling. So this is a nice group of people for us, for you guys who are working with ocean modeling. And so thank you very much for participating in this. We did get some questions, Ingrid, and we will take that in the dialogue part when we are discussing at the end. So, so keep on asking questions and comment also in the chat. We will take that up after all the presentations. So thank you very much. Now, the next speaker will be talking about specifically a huge investment in Europe on ocean capacities and resources. Sylvain Cailleau, welcome. He is an oceanographer also, and he is working on a team in Mercator Ocean International on evolution of the hindcast and forecast systems. He has a long experience in this area and work also on different types of applications of ocean modeling. For instance, sargassum, which we have talked about, Sylvain. I was doing some in situ observations in the Caribbean in the Easter. Of course, he is talking about Copernicus services, and he's involved in the new investments in the digital twin and the model side of that in the EDITO project, which we are very happy to collaborate with here in ILIAD. So Sylvain, we are happy to have you here and looking forward to your presentation.
Okay, thank you. Sorry, wait a minute. Okay, can you see my screen?
Now we see even a slide, the first slide.
First slide, okay?
Yes,
Okay.
full slide.
Thank you all, and good afternoon. So I'm going to talk about the Copernicus Marine Shell Service, a short overview of this service, the modeling, the ocean modeling associated to this activities to these services, and the link with EDITO, the digital European digital twin ocean, and the link with ILIAD project. So Copernicus is an Earth observation program of European Union. It's composed by 6 components for land, for atmosphere, for climate change, for security, and for emergency, and for marine. And the Copernicus Marine Service is funded by European Commission and implemented by Mercator Ocean. And it consists in a web portal which provides free, regular, systematic information on the state of ocean. We can divide ocean in 3 colors, 3 domains, in fact: blue ocean for physics, white ocean for sea ice, green ocean for bio. So you can find the products of these different color ocean in the web portal of Copernicus Marine Service. We can divide the ocean in different areas: global ocean, the Arctic Ocean, and the European regional seas. And for each areas, different organism, private organism or public organism in Europe organized in a consortium in order to develop monitoring system and forecasting systems in these different areas. The different numerical models are assimilated with data observations, and they reach horizontal resolution from 10 kilometers to 1 kilometers. It depends on the areas you consider, and the vertical resolution from 1 meter in the surface to 500 meters at the bottom. And we consider products, model products in the past with the multi-year products, and in the future with the forecast products. For the forecast products, they come from the result of the ocean model, deterministic ocean model. But we expect in the future for this service to provide also products from ensemble systems, stochastic systems too, but in the far in the future, of course. It's not ready now. The forecast follow daily cycle, and the forecast leads in 10 days. Regarding multi-years, products, they extended from 1992 to 1 or 2 years before present. New time series are provided every 3 or 5 years, and the time series are regularly extended. Regarding the blue ocean for physics, user can find in the web portal the temperature variables, salinity, currents, sea level, mixed layer depths, and waves. For the green ocean, user can find nekton data, plankton, organic carbon, nutrients, oxygen, carbonate system, and optics such as ocean colors. And for white ocean, users can find sea ice concentration, sea ice extent, sea ice thickness, sea ice type, sea ice velocity, snow thickness, sea ice albedo, and sea ice age. All these products are rigorously assessed. Each new products or updated product are assessed, of course, and even during the operational providing, there is a monitoring of in a real time of each products. Regarding the different products for forecasts, there are 23 products for blue ocean, 4 products for white ocean, and 7 products for green ocean. And regarding the multi-year products, there are 12 products for blue ocean, for physics, 4 products for sea ice, and 6 products for bio. The number of users is steadily increasing every year since the beginning of the Copernicus service. And forecast product has a slightly higher number of users than multi-years one. We can reach in totally about 20,000 users in 2022. Yes, there are, in fact, for each areas, each consortium that I presented before, which who developed different models for the forecast products, use different models for bio, for ice, for wave, and for physics. And for each area, there are different models too for these different components. And these models are connected by a coupling method or forcing method. But finally, even if there are a strong diversity of models, you can converge to the standard products, which follow the same format, file format, the same metadata, the same standard name for variable, and so on. And the Copernicus service brings about a lot of downstream services with a strong link with the coastal application. And you can see in the website of the Copernicus Marine Service a lot of examples of the use cases. For instance, regarding the harbor safety, the ensemble multi-model has been developed for sea level forecast at the Spanish harbors. So we consider many models in the overlap zone, and we can provide a kind of ensemble forecasting. And this ensemble forecasting provide better forecast than any individual members. So, and another use case is the sargassum, the monitoring of the sargassum drift and beaching monitoring in seasonal forecast system. You can find this kind of system in the 4C project website, which provide monthly sargassum drift in the equatorial Atlantic. And sorry, I answered to the question. And this model, there are 2 components in this kind of forecasting model: physics and sargassum model, evolution model. The physics model is forced by Copernicus Global Ocean Forecasting System, and the sargassum detection is initialized by MODIS satellite remote sensor data. And soon it will be replaced by, probably replaced by new data from Copernicus of detection of sargassum. Up to now, the system is operated in best efforts, but we plan to make fully operational this system. And it will be a demonstrator, use case demonstrator for the future editor. So to conclude, Copernicus Marine Service is a complex and mature system since 2015 with a continuous evolution. And we expected an increase in resolution. We expect to provide ensemble forecast with uncertainties associated. And we plan to improve the link with the European coastal forecasting system for downstream services. And so finally, Copernicus Marine Service is one of the cornerstones for EDITO, for the European Digital Twin of the Ocean, where the downstream services developed in the framework of the ILIAD project, for instance, will be plugged in to this cloud platform. Okay, I finish. Thank you.
Thank you very much, Sylvain. And indeed, there's a lot of resources to be used out there. And I really like that you were looking at how the relationship between the different twins that we are developing in ILIAD are linked to various products that you are providing through your community. So that was great to see. I have also posted a poll, and I will end the poll. And I don't think I shared the results with you the last time, so apologies for that. But now you will see the results. We asked you if you would be interested in high resolution ocean models. So both Ingrid and Sylvain talked about that. And there's a clear and loud yes. 74% here are interested in both spatial and temporal high resolution ocean models. Some are interested in the spatial only, and some also only in temporal. And I think the answer here is quite clear that this is top. This is the top interest area for this audience. So thank you very much again for participating. And again, the questions, and I think you should use the opportunity to ask questions in the chat, and we also have some questions, of course, to ask each other, both speakers and myself, but it would be great to hear your questions as well and comments so that we collectively learn more. Thank you, Sylvain. And now I will introduce some, and now these two first presentations were more on what resources we have to use here in Europe. And now we are going to look more on a couple of examples on how they are being used. So with that, I will introduce the next speaker. She is one of our partners in ILIAD, Katerina Spanoudaki. She is an engineer, but also involved in concrete operational ocean forecasting systems. She is particularly interested in oil spill and has expertise and worked on pollution, various questions related to pollution. And I think with that, Katerina, we are ready to hear about your example. So I give the floor to you. Stop sharing and give the floor to you.
Thank you, Bente. Okay, hello everybody. I'm Katerina Spanoudaki. I'm working at the Foundation for Research and Technology in Greece. And in the frame of this webinar, I will talk a little bit about the Lagrangian models, the particle tracking Lagrangian models that we use in ILIAD. Okay. So in ILIAD, we have several thematic digital twins, as Bente mentioned before. We have more than 20 pilot digital twins in several thematic areas. And in some of those, we do use numerical models that are Lagrangian models and are used for pollution forecasting. And there are cases, for example, in Thracian Sea and in Cretan Sea for oil spills. And we also have in North Sea for microplastics modeling SINTEF actually. So coming a little bit to the example I will share with you, which is for the Cretan Sea digital twin. We are focusing on oil spills, and the motivation for using these particular numerical tools for our area is because it is an area of high economic interest, and there are very recent exploitation activities for offshore oil and gas. So we do have a large community of stakeholders which are interested in this kind of DD virtual environment. What we want to develop, or what we have already tried to develop, is to have some novelties and some novel features for the thematic digital twin. So this includes an analysis of Earth observation data for an automatic triggering for our oil spill models when there is an oil spill event. We use high-resolution metocean forecasting in order to be able to obtain forecasting predictions at coastal scales. And we're able to use backtracking to link pollution events to potential sources, and also use our digital twin as a virtual environment for producing scenarios, so predictive what-if scenarios that our stakeholders might be interested in. In any case, if one wants to simulate an oil spill event, there are some specific questions that need to be answered. So the response authorities wait to hear from us where the oil spill will move to, how soon it will get there, which are the resources that are threatened, and at what state the oil spill will arrive. The first three questions are very much related to metocean forecasting, so we need reliable and high-resolution metocean data to answer these questions. But to answer the fourth question, what is the state of the oil when it reaches a coast or a vulnerable coast, we need to have reliable, well-documented fate algorithms in our oil spill models. Sorry. So what are these algorithms? They try to simulate what will happen to the oil when it reaches the surface of the ocean. And these processes include evaporation, spreading, first of all, evaporation, emulsification, dispersion into oil droplets in the water column, and sedimentation, and of course, always they're transferred by the sea currents and the wind. Some of these processes are more quick to happen, and some processes take a longer time, but they do have a large impact. For example, biodegradation is one of the processes that is not very often modeled. However, it is one of nature's ways to attenuate the impact of oil spills. So what we need in our models are some metocean variables, environmental variables like winds, current, and waves. We need to know the type of oil that is spilled in our models, and then we simulate the fate and the weathering of the oil spill by evaporation, dispersion, change of viscosity, etc. And of course, all of these are simulated by solving the diffusion equation, assuming that the oil is a number of, or an aggregation of particles. This is the sense behind the Lagrangian model. So we do get then the oil slick transformation and the different compartments of an oil spill. So if it reaches the coast, how much remains in the surface, how much is evaporated, so on. As I mentioned before, it is very important to have a reliable and high-resolution metocean data in order to be able to simulate where the oil spill will move and how soon it will reach the coast. So for the Cretan Sea pilot, we use high-resolution hydrodynamic, actually it's NEMO, and wave models is WaveWatch 3 and SWAN for nearshore wave dynamics. We also use WRF for producing high resolution weather forecasting. And our hydrodynamic models are actually nested in Copernicus marine products. So we go from a coarse resolution to a high resolution around 1 kilometer for the coasts of Crete. The system is daily, has been long-term calibrated and validated. It's also daily validated using satellite data and using available buoys for the waves in order for us to be able to know that we get concrete forecast and results. Sorry. Regarding the oil spill model that is coupled to the metocean forecasting system, it's an open source community model. It's called MEDSLIC2. It has been developed by several institutes in Europe, and it's hosted by UNIPO, so it can be freely downloaded. It uses oil spill properties data, atmospheric data, oceanographic data, solves, as I said before, the advection diffusion equation using a Lagrangian format, and it forecasts the oil spill transport and transformation, so the weathering. We are working also in several research issues, so we are interested to change or enhance the weathering algorithms of the oil spill model. So basic shortcoming that we are addressing is that it uses some algorithms that address the oil as a uniform substance, so it does not differentiate between different chemical constituents. And since oil is a very complicated mixture of thousands of various types of different chemicals, we have developed several subroutines where we treat the oil as a mixture of pseudo components. So in each component, we aggregate all the constituents that appear in the same way or behave in the same way. And in this manner, we are able to track the fate of each pseudo component separately, depending on the evaporation rate or the biodegradation rate. So we treat, for example, alkanes or aromatic hydrocarbons in a different BC. In order to test this new model or the enhanced MEDSLIC2 model, we have applied it, for example, in the well-known Lebanon oil spill. It happened in 2006 during the Israel-Lebanon conflict. So we have separated the oil in different components defined by distillation cuts in order to be able to track how different alkanes and aliphatic components, aromatic components would behave. What we have found is that we have tracked first of all the surface leak, how it moves and how it compares with satellite observations. But we have also found that there is a large quantity of oil that remained in the water column, and finally it sedimented, or we found it on the coast. These are the heavier components, so around 32 tons of the total oil that was in the water column did biodegrade by the bacteria, but the rest of the oil did remain in the water column, so it would be digested by marine organisms, etc. So it's very important to be able to track this separately. Another issue that we are keen on working on is for tracking the fate of subsurface oil jet and plumes. So we have also developed such a sub-model for MEDSLIC that not only models the jet and the plume, but also the biodegradation of the different droplets. Go through quickly. So we have tried to verify this model in order to be able to include it in our digital twin. And we tested it with an in situ experiment, which was conducted by SINTEF in North Sea, actually. And we really did see that we managed to have very good match between what was observed in situ observation with our model. So the rise time of the plume and of the droplets and what was measured actually in the field experiment by SINTEF. We are also doing a lot of experiments in collaboration with Technical University of Crete in order to be able to transfer very high pressure seawater with indigenous bacteria from the sea to the lab and see how quickly a native bacteria would biodegrade the oil if an accident was supposed to happen in the south of Crete. So we did see that if we had such a case, if we did not treat the oil with dispersants, it would rise very quickly on the surface onto the shore and would pollute quite along the shoreline. While if we do treat with dispersants, we will have the bacteria feed on a larger area, and this would make the effects of such an oil spill not so severe. In terms of the virtual environment of RDT, we would like to see, we would like to develop, let's say, an oil spill simulator since the model can work for the global ocean. So the user can enter the DT and insert several the oil type, choose if he wants to use high resolution data or data from Siemens from the global ocean or in SINTEF winds or local winds, and then they can produce a simulation and see how what is the effect on the coastal zone. And finally, what we're also working at is for detecting oil spills from Earth observation and trying to see if we can directly ingest this and train our oil spill model. I can see Bente smiling, which means I'm talking a lot. So, but that's it, I'm done. Thank you.
Thank you. Thank you, Katerina. That was in the Einstein relativistic universe. That was could have been 5 minutes, maybe. Thank you, Katerina. It was very interesting. It's very interesting to see how numerical models are being combined with ocean models in general and how it can be applied on very, very important issues for all of us. So thank you very much, Katerina.
Thank you.
Again, questions. I do see that there are some questions in the chat. Thank you very much. But before we move on to the last example and we start the discussion, let's see how we did in the poll, where we were asking, are you used to work with numerical models like Katerina? And indeed, almost 60% of you are using numerical models frequently. Almost 20% would like and need to learn more, and 24% do not use that. But you see that there's quite a few using quite numerical models and want to use numerical models. Now, for another example, where we are also including citizen science, by the way, we are going to talk about jellyfish warning. But first, I would like to introduce, of course, our speaker, the expert, Paulo Chambel Leitão from Hidromod. He's a researcher, he was a researcher at the Instituto Superior Técnico in Lisbon, but now he works and has been working in Hidromod for quite some time. He has expertise on implementing and validating hydrodynamic coastal numerical models. He's using numerical models in operational forecasting systems and generally interested in operational modeling, mass transport, etc. Paulo, the floor is yours. We are excited to hear about the jellyfish example.
Okay, let us see if I can share my presentation. My presentation is entitled Jellyfish Clogging Events, a Particle Tracking Model Approach. In reality, it's the citizen science and the particle tracking model approach. I work in Hidromod. my presentation will be more a practical one. Basically, we have a problem in Israel that there is a lot of desalination plants in the Israel coast. You have a lot of power plants that use sea as a cold source to the refrigeration system. So these are infrastructures that are very critical for the state of Israel, and they depend on the behavior of the jellyfish, because jellyfish tend to clog these systems. They usually these industrial facilities, they pump a lot of water, and some of them, the nuclear ones, cannot be shut down. So this is quite a problem. I think I've done take some frames in from this YouTube video that is explained very well the problem. So you can have these jellyfish swarms events that they are huge. Then when the intake, if you have an intake that pumps 10 cubic meters per second, you have this jellyfish coming to the intake, clogging the intake area. In this case, you have a system, a very complex system that basically uses clean up the intake area, brings the jellyfish up, put it in the channel, then put it in these big boxes, and then a truck take it away. So this is system. It's a big problem. There is a lot of money put to avoid this problem, and this is what we want to allow to improve the operation. This operation. So our main goal, our ideal goal, was to give them some kind of alert so they can be prepared for the event. In the base of this work, we are using citizens. We are based all the work in this citizen science monitoring program. A very good citizen. Basically, it has a web app. It's been working since 2011. It has in the database more than 20,000 reports. With a lot of information about the species at distance from the coast, the density a lot. It has an army of almost 5,000 users submitting reports. They usually it's in a daily base, and 500 trained that are more experienced and then are able to give better information. This is all. We are. There is a lot of formal science behind this. The Dory team has many papers where they try to base this crossing the citizen science with the numerical models, particle tracking models, DNA analysis. There's very extensive literature done by this team that is supporting us in our efforts. Okay, what is the ILIAD goal? Basically, is, as I said already, to support water intake operations. Basically, we want to provide a platform where we can merge the citizen science observations with the particle tracking model. We are working in ILIAD with other pilots. We are working also with an aquaculture pilot that is focused in aquaculture in Italy, another in Tunisia, and ocean engineering in Scotland. So I'm going to only talk about Israel jellyfish case. We have already a site where you can play with the tool. So our general methodology will be to use citizen science observations, the knowledge of the Dory Edlis team, and use the marine Copernicus that you have already a nice presentation. In this case, we are using the MedSea forecasting system. Use this forecast. Now we are only focusing the surface currents, but we want also to look at primary production, temperature, etc. And then run a particle tracking model where we can, in the observations location, define an emission and to see what can be the trajectory of inert particles that are transported by the surface currents. This is our starting. It's not the starting. We have already done some work. So what we want to deliver in this first step, a platform, what we call it, which will be our basic goal. It's this platform that is able to do forecasts. This is a forecast that I done for today, one day forward. And we want to add to this platform, already working, a link to the database, the citizen science database. So, for example, the user can see what in the last 15 days, what was the observations, and do some kind of hypothesis, and to see, okay, if this guy in a kayak observes something like this, it's a big swarm, where the MEMS circulation model says that it can be transported. It's near a desalinization, near a power plant, a beach, whatever. But our final goal was to have this platform, but also to have some kind of alert system that, based in these particle tracking trajectories, based in temperature, that it's a trigger, because if the temperature is too high, the jellyfish tend to die and then to be transported. It's not able to have an agency to be able to go against the current, so it can be transported to the coast. So the idea was to do enough. So how are we going to try to forecast these clogging events? This is under analysis, but our focus is to do statistical analysis of particle tracking, temperature, and particle production model results. Now we are focused on the particle tracking. There is literature that connects the Nile area, the Nile coastal area, with the Israel. So apparently, it looks like the jellyfish, the origin of some of the jellyfish is the Nile, is this coastal area near the Nile. Makes sense because it's a source of nutrients. So it makes sense. So what we are doing is we are running a particle tracking model. We are emitting in the Nile area particles in the offshore area, in the coastal area, and to see how the particles are reaching the coast and the shelf, and to see if the time variability that we are getting and makes sense with the citizen science observations. For example, if we cross for particles emitted in the specific area, we are able to have this increase in density particles reaching the coast in the same time that there were reporting these events in the media. So this is something that we are analyzing, and we are going to go to temperature. But this, we don't know if we will be able to do it, but it's our effort to have an alert that can be sent whenever there is the conditions, the meteorographic and biogeochemical conditions for a clogging event. So this power plants and desalination can be ready we have implemented many forecasting systems in various areas in the world. And for example, this is very similar with the system that we had for macroalgae. Again, and this helped a lot the power plant to organize their activities and to be ready for the problem. Okay, thank you.
Thank you very much, Paulo, for showing us a very interesting example.